get started with parts per billion examples. So parts per billion means highly concentration or low concentration? What do you think?
Could it mean either or?
Nope, it's only one. So think about that. Think about what that means. Parts per million, parts per billion.
Low concentration?
Very low, extremely low. So parts per million means you have one part for every million parts, right? Or 1 gram for every million grams, 1 milliliter for every million milliliters, or whatever, okay? So for example, we have 35 micrograms of chloride in 4 kilograms of tap water. Uh-oh, we have a problem with the screen, sorry. There we go. So 35 micrograms of chloride in 4 kilograms of tap water. And we want to know what the concentration is in parts per million or parts per billion. I say or because, well, we don't know. Is that concentrated in parts per million, or is it better to write it in parts per billion? We'll find out as we go. Okay? All right, so let's just, since we got to know parts per million, parts per billion, how do you find it?
Conversion factors?
So I gave you guys a kind of an equation last time, right? So concentration is always measured in, what's the equation for concentration in general? If you know this, you don't have to memorize every equation. I mean, you can memorize every equation if you'd like. Solute over solution, right? Amount of solute over amount of solution. Write that down. Any concentration is equal to the amount of solute over amount of solution. Now let's think about, I didn't talk about this last time. Why is solution on the bottom? Any ideas? Why is the amount of solution on the bottom of this?
Because the solution is both solvent and
Yeah, it's
solvent.
all of it. It's the whole thing, right? And whenever we find a fraction, it's out of the total, isn't it? Or percentages, it's out of the total. Okay? So, and when we say we have chloride in the water, what are we interested in here? Are we interested in water? No, we're interested in chloride, right? Chloride is the solute, and we're always interested in that solute. In our solution, we name the solution after the solute, right? Okay, so it's solute over solution. Always, always, always. When we talk about molarity, that's what it is. When you talk about mass percent, volume percent, mass to volume percent, parts per million, parts per billion, it's all amount of solute over amount of solution, okay? All right, so if we're doing parts per million, parts per billion, we don't know what it is yet, right? So what are we going to do? What is the solute here? How much solute do we have? 35 micrograms of chloride. That's our solute. Now what's the amount of solution? How much solution do we have? Is 4 kilograms solution or solvent? How do we know? Because it's tap water, and tap water is not pure, right?
Right.
Tap water is a mixture. It's a solution, okay? So we got 4 kilograms of H2O, of tap water, okay? I should call that tap water because it's not just water. There's my solution. All right, now I got to determine if I should multiply this by 1,000,000 or 1,000,000,000. How do I do this? Any ideas?
I guess we could go with the, should we try 1,000,000?
We could. We could try, but we got to do something before that. What are the units of parts per million, parts per billion? It's just parts. No grams, no liters, no moles, no, it's just parts. It's parts per million or parts per billion. And we have units here. What does that tell us we got to do? Get them to cancel. You with me? Well, we have micrograms and kilograms. Do they cancel?
They can cancel.
Not yet. What do we have to do? Convert them to what? Yeah, the same, right? Either convert micrograms to kilograms, kilograms to micrograms. What I would do is convert both of them to what? Grams, because we know that conversion factor, right? So let's just convert these. Let's convert micrograms first. Is that okay with everybody? It doesn't matter what you do first. So micrograms to grams. Which one's bigger? Grams. So we're going to put 1 gram. How many micros is the same as 1 gram? 1,000,000. 10 to the negative, 10 to the negative 6, or 1,000,000th. So how many millionths is the same as 1? 1,000,000 millionths, right? Yeah, you had it right. Just make sure you don't put 10 to the negative 6 down there. If we do it that way, we could write it like this. 1 microgram is 10 to the negative 6 grams. We can write it that way. Make sense? Are you guys okay with just writing 1 here and 10 and 1,000,000 on the bottom? What? Or you can do 10 to the 6. Yep, that works. Okay? Are we good there? Okay, what cancels? Micrograms, right? Now we have grams on tops and kilograms on bottoms. So we got to change either grams to kilograms or kilograms to grams. And we decided to just change everything to grams, right? Doesn't matter what you do. Do it whatever way you think of. Okay, just make sure you're using the right conversion factor. So kilograms goes on top, so it can cancel. Grams goes on bottom. Which one's bigger? Kilo. So there's 1 kilogram. How many grams? 1,000. And kilograms cancel, and so does grams. So all the units cancel here. So what do we need to multiply by to get a relatively small number? Because we don't want a huge number in scientific notation if we don't have to, right? Or huge or small, right? So what number makes most sense to multiply, 1,000,000 or 1,000,000,000? Why? 1,000,000 and 1,000 multiplied together is 1,000,000,000, right? So if we multiply by 1,000,000,000, then that and that cancels with that. And if it doesn't work out so wonderful like this, guys, no big deal. Plug it in your calculator before you do this, and you get an answer. And it's going to be something times 10 to the negative something, right? It's going to be small. And you just cancel, okay, if it's -9, it's billion. If it's -6, it's million. What if it's -10? What are we going to mark it as? Parts per million, parts per billion?
Parts per billion?
Parts per billion is closer to billion, right? Does that make sense? And we do this and we get 8.75, should be 8.8, rounded to the right number sig fig, actually. Should we do 9? That's only 1 sig fig. 9 parts per billion. Good? I mean, if you did it in the calculator, it's 8.75, right? Did I calculate that right? Did you guys do that? Because sometimes I make mistakes too. And if I made a mistake while doing this, well, it's there permanent for now. Questions? No? Okay, let's do another conversion. Let's say, let's say we have we have a solution of 0.360 molarity of potassium dichromate. And we want to know, and this is an aqueous solution, and we want to know the mass to volume percent. What should we do first? We're just converting. What do we have right now? Molarity. And what's another way to write molarity?
Moles?
Almost. Mass over volume. It's not just mass over volume. What units? Because mass over volume is density. Moles over liters, right? And that is mass and density. You're right. So is molarity is concentration? We talked about this last time. Is that the same as density?
No.
It's not. It looks like it. For molarity, it looks like it. Well, hold on. Moles isn't mass. But can you convert moles to mass? Is it amount of solute over amount of solution? If you're talking about a mix or a solution, then I guess it is. But density is mostly, in fact, I've never saw it any other way. When you measure the density of something, it's pure substance, not a mixture. Okay. So density is a physical property, and you can change the density of a solution by depending on how concentrated it is, right? So we have let's change colors for a minute. We have 0.360 moles of K2Cr2O7 per 1 liter of solution, right? That's what molarity means. And we got to do mass per volume here. What does mass have to be measured in? It has to be measured in grams. And what does volume have to be measured in?
Liters.
It has to be measured in milliliters. Who can tell me why? And this only works for aqueous solutions. Do you remember anybody? 3 of you might not have been here last time, so here we go. I'll just tell you. So when we do mass per volume percent concentration, the mass has to be measured in grams. The the volume has to be measured in milliliters, and the reason why, do those cancel out? Grams and milliliters?
No?
They do not cancel out unless it's for water, because water has a density, which is mass over volume, of 1 gram per 1 milliliter. So if it's a water solution, then they do cancel, because they're the same, right? That's why if we do mass per volume percent, it has to be grams and milliliters. Can you remember that? I know you can, will you? All right. So we've got to change moles to what?
Milliliters?
I don't know. Can we do that? Do we have something to go from moles to milliliters? If it's a gas, we do. Is this a gas?
No.
How do you know?
Because it's an
It's an aqueous solution. It's a liquid solution, right? Okay. So we can go from moles to what then? Grams, right? Let's change the top guy to grams, right? So if we have 1 mole of potassium dichromate, what's the mass of that? Potassium is 39. And we've got to multiply that by 2. Chromium is 40? 52, I was way off. Okay, I was thinking something else. That's why you don't try to memorize this, guys. Use your periodic table. Times 2 plus oxygen is 16 multiplied by 7, right? And what do we get? What's the molar mass? If my calculation's right, it's 294 grams per mole. We good? Good enough? All right, so we're going to put 294 grams of potassium dichromate on top. Moles goes away, and we have grams on top. That's good. Now we got to have milliliters on bottom. And what's the conversion factor? Somebody tell me. I'm not going to tell you. I won't tell you on the test either. 1,000 what? Liters? Milliliters goes where? Top or bottom? On the bottom. And 1 liter on top. Are we good? And now we have grams per milliliter, and since this is an aqueous solution, we can cancel those out, right? All right. But what unit do we need? Mass over volume percent. So are we done? Any percentage, you have to multiply by the fraction by, or a decimal by 100, right? Times by 100%, and we should get 10.6% potassium dichromate. Does that make sense to everybody? Question?
How did you cancel the grams of?
Oh, the grams?
Yeah.
Yeah, that doesn't look like you should be able to.
But it's an
But
aqueous.
since it's an aqueous solution, and water has a density of 1 gram per 1 milliliter, they're the same. 1 gram of water is equal to 1 milliliter of water. So they're the same unit, right? Or if that doesn't resonate with you, then don't do that. Do this. We know the density of water, and then you just have to do one extra step though, right? We know the density of water is 1 gram per 1 milliliter. And then grams cancel, and milliliters cancel. But we didn't multiply anything but 1. Does that make sense?
Yeah.
Okay. And then times by 100. So I'm glad you asked that. Thank you. Does that make sense to everybody? Any other questions? If there's not any questions, I'm going to move on to today's topic. Yeah.
So that just means there's 10.6% of that in the whole solution.
Uh-huh. So the whole solution is
For
solute and solvent, remember? Were you here when we talked about?
No.
Okay. So a solution is made of a solute and a solvent. It's a homogeneous mixture. Was he here when we talked?
Yeah, I was.
Okay, yeah. So it's just saying we have 10.6% of the solute in that solution.
And the solution is 0.360 m.
Molarity.
Molarity.
And that's just so we converted from one type of concentration unit to a different type. That's all we did
Oh,
here.
okay. So we
That's
don't
all.
actually know how much is, how big the solution is itself.
How much volume? No, we don't.
No.
This could be a 10,000 gallons or it could be 1 ounce. But the percentage stays the same, right?
Right.
Yeah. Are we good? Anything else? All right. So today we are putting it all together. Everything we've learned for the whole semester so far is right here. Okay? So first of all, let's just give you a scary word. Because this is, I don't know why we use this word. It just sounds icky. Okay, but here we go. Stoichiometry. And really what this means is the quantitative relationship, do you guys know what quantitative means? Yes, no? Quantitative has what word in it?
Quantity?
Quantity, and quantity means what? How much? Right? In number-wise. Okay? So it's the quantitative relationship between two or more substances in a chemical reaction. And I should write here in parentheses, this is just the math of chemistry, but it's to make predictions. Anybody scared because I says it's the math of chemistry? We've been doing this math the whole time. We did it just barely. It's called dimensional analysis. Okay? I'm going to show you one last step, and then we have all of the pieces and parts that we can use to make predictions in a chemical reaction. So this is the main thing that we do here in chemistry, okay? For this class anyway. Good? No, I think it is anyway. All right, I'm going to give you the mole roadmap. So we talked about how to convert moles to moles, or moles to grams, and grams to moles, and moles to particles, and particles to moles, and moles to liters, and liters to moles, right? Talked all about that stuff. Now I'm going to just show you how to go from moles of one substance to moles of a different substance. That's today's topic. That's what stoichiometry is. So let's write that down. We use stoichiometry to convert from one substance to another substance. For example, if we had, in fact, when we did this reaction, we had sodium, and what did we do with the sodium? We threw it in some water, right? And it reacted and it exploded. Well, why did it react? Because it had hydrogen gas, and hydrogen gas is explosive. It produced hydrogen gas, and there was enough heat in there. It was an exothermic reaction. You heat that hydrogen gas and it explodes, and then we're left with sodium hydroxide. which is a base. Well, I've talked a lot about that yet. So if we want to predict, well, how much hydrogen gas will we get? Well, what is this? This is basically a recipe of how we get it. Now, there's something wrong with this recipe. Who can tell me?
No quantities?
Kind of, yeah. It needs to be balanced, right? Now listen, I'm not going to teach you balancing right now. It's not going to be on Unit 3 test. It's going to be on Unit 4 test. Why do we do it this way? I have no idea. But
Well, I mean,
I don't have enough time to show you how to do balancing equations. It's not that difficult. In fact, I can show you on this one. But there's a whole bunch of tips and tricks that I can give you to make it well, right? So right now, this is just a list of ingredients. You need these two ingredients on the left, which are called what?
Reactants.
Good, reactants, because they react together, right? Does that make sense? You should write this down. And what does it make on the right side?
Product.
Products, because it produces the products, right? Does that make sense in your mind? Okay. So we just have a list of ingredients here. This is a chemical equation. But to make a recipe, and really, if we want to figure out how many cookies we're going to make, we got to know amounts, right? So we got to know this. So here we go. How many sodiums do I have over there? One. How many sodiums do I have over there? Oh, that looks pretty balanced, right? Same on both sides. How many hydrogens do I have on this side? Two. How many do I have on this side? Oh, we got some right there and right there. There's 3 of them, right? It's like, how's 2 and 3 going to balance? Let's try it later. There's 1 oxygen here, so we got to do it. Here's a little trick. You don't have to know this right now. We'll talk about it later. But there's always going to be an even amount of hydrogens on the left side. If we have more water, there's going to be 2 for every water, right? So there's always going to be an even amount on the left side. And right here, there's always going to be even plus an odd is always an odd. So let's make this even. If we have 2 of those, well, now we have 2 sodiums, so we have to do 2 over here. 2 oxygens, so we have to have 2 over here. And here we have 4 hydrogens on the left. 2 plus 2, that's 4 hydrogens on the right. And now it's balanced. Okay, ladies and gents, I'm not going to test you on this unit. Okay, if I give you an equation, I will give it to you balanced. But these coefficients right here, you guys know what a coefficient is? If I say 3x, what's the coefficient of x? 3, right? Do you remember doing that in math? Okay, it's just the numbers out in front. And to follow the atomic theory, which says in a chemical reaction we don't lose or gain any mass, right? Stays the same. So that's why it must be balanced. All right, so let's go ahead and give you a mole roadmap to help you to know how to convert from one substance to a different substance. And we'll do plenty of examples here, okay? I'm just going to give you this mole roadmap, and on the reference sheet that I gave you for the midterm, it has this mole roadmap on there. So if you have, do you guys have a copy of that I gave you? With the electronegativity chart? It's on that sheet, okay? So, but write it down anyway, just to make sure you understand it and take notes on it, right? All right, so let's go ahead and write this. This is the mole roadmap. And this will tell you how to convert from one thing to the next thing, okay? All right, so let's start with, let's say we have grams of substance A. It could be any substance, right? I'm just calling it A. Is everybody okay with that? If we want to convert from grams of substance A to, let's say, moles of substance A, do we know how to do that? What's the conversion factor?
One,
What is it?
1 mole per gram.
What is moles over grams? What's that called?
Grab the molarity of an element.
Not molarity, but
Is it molar mass?
molar mass, right? Yeah, you got it. But molar mass is the conversion factor to go from grams to moles. And what if we want to go from moles to grams? We just flip the molar mass, right? Well, actually, if we go to grams to moles, we flip it. Okay? Are we good? And then I can also go from moles of substance A to particles of substance A. Do we know how to do that? What's the conversion factor?
The conversion factor is from 1 mole to 6.022 x 10 to the 23rd.
What does the X mean?
Multiply.
Times.
Yep, that's right. So Avogadro's number, right? That many is equal to 1 mole.
Yeah.
Are we good? Okay, then if we want to go from moles of one substance to moles of a different substance, let's say moles of substance B. Now this is the part that I haven't showed you yet. So this is just the mole to mole ratio from balanced equation. So you have to have a balanced equation in order to do this. And I'll show you how to do that next unit or next time. Because we have a test coming up this weekend, right? Do you have to do it this weekend? No, don't do it if you're not ready. Please don't. But don't take 2 weeks to do it, okay? That's all I'm saying. You guys know what your situation is and do what you got to do. Study and get ready for this before you take it, okay? All right, and especially if we don't finish the material. I think we will, but we'll see how it goes. All right, so I'm going to just finish drawing this mole road map, and then I'll show you what that means, okay? Then we can go from moles of substance B to grams of substance B. And what do we use? Molar mass again. It's the same thing, it's just a different substance, right? We can do it to all these substances, right? And then we can also go from moles of substance B to particles of substance B. And when I say particles, what are the different ways to call particles? Ions, atoms, molecules, and formula units, right? Are we good? And then this, we just use Avogadro's number again. And again, this is on your reference sheet that you will have on the final. But write it down, practice using it, and if you practice using a lot, you probably won't even need it on the final, right? You just do it. But whatever. All right, so let's talk about this right here. Mole to mole ratio from the balanced equation. So I'm going to write this equation again. We had 2Na plus 2H2O. Is that what we had? Yeah. Gives us H2 plus 2NaOH. Is that what we had? Yeah, okay. So what this is saying, what do we have? 2 what? 2 sodium what? Atoms? We could. For every 2 sodium atoms, we have 2 molecules of water. We get 1 molecule of hydrogen gas and 2 formula units of sodium hydroxide, right? But gosh, do we ever deal with just particles? Never. We never do. Remember I said, this is not useful to convert with this, but we do it so that we can do what we're doing today. And let me show you what I mean. We can say this is 2 moles of sodium. And we can say that this is 2 moles of water. And we can say this is 1 mole of hydrogen gas. And we can say this is 2 moles of sodium hydroxide. You with me? Why can we say that? Because if we have 1 mole of anything, doesn't matter what it is, we have 6.022 times 10 to the 23 particles of that thing. So when we go from particles and moles, we can interchange them because of that ratio. Does that make sense? And that's why we need to know 6.022 times 10 to the 23. Okay? That's the only reason. But you will have to know how to convert from grams or moles to particles and particles to mole on the test, right? But that's why. In real life, you probably won't ever do that. Okay? But you will do this if you're going to be a chemist, okay? All right, so this is saying for every 2 moles of sodium, we have 2 moles of water. It's also saying if we have 2 moles of sodium, we have 1 mole of hydrogen gas. And it's also saying if we have 2 moles of sodium, we have 2 moles of sodium hydroxide. Do y'all understand how I got those? For every 2 moles of sodium, I have 2 moles of water. For every 2 moles of sodium, 1 mole of gas, hydrogen gas. 2 moles of sodium, 2 moles of sodium hydroxide. And what can I do with these conversion factors? Flip them. So I got 6 just for that one, right? Is that all I have? Can I do for every 2 moles of water, I have 1 mole of hydrogen gas, right? Right here. That's it. So I got a lot of different conversion factors just for my balanced equation. You with me? Because I can go from sodium to water. I can calculate sodium to hydrogen, sodium to sodium hydroxide, or any other substance, one substance to a different substance. Doesn't matter. Does that make sense to everybody? Or does that, it's like, whoa, what is he saying? Anybody feeling that way? You feeling, what is he saying? Okay. So let's do a problem. So rather than writing all those out, just know that we can go from one substance to a different substance. And so on this balanced equation, on this mole roadmap, it says use the mole to mole ratio from the balanced equation. That's this, mole to mole. There's the mole to mole ratio from sodium to water, okay? So ready for an example? Yeah? Anybody else feeling like it's, whoa, slow down? Is that okay? Make sure you understand this fully before you leave today. And then go home and study it before 24 hours is up so you don't forget it. I feel like some of us are doing that. But let's do another one. Let's say we have 2H2 plus O2 gives us 2H2O. So I'm always going to give you a balanced equation until next unit. Then you'll have to balance it, okay? And let's say I start with 10 grams of hydrogen gas, and I have excess oxygen. What does that mean? Excess oxygen.
Like,
Unlimited, right? I get it from the atmosphere, and I have plenty of it. It's never going to run out, okay? Plenty of it. Enough to react with 10 grams anyway, right? More than enough. And I want to know, how much water will I make in grams, for example? Okay? All right, so where do we start?
2 moles of hydrogen over 1 mole of oxygen?
Not quite. Do you remember doing dimensional analysis? It's the same process. This is dimensional analysis. What's the first step in dimensional analysis? What are we looking for? What are we looking for here? Grams of H2O. That's what we're looking for. Right? Does moles of H2O do us any good? No, I don't know what that means. I can't measure that, right? Okay? So yeah, grams of H2O. That's what we're looking for. What's the second step? What do I know? Yeah, what do you know? We know that we have 10 grams of hydrogen gas. Are we good? Doing okay?
Yeah.
Okay. What's our next step? Did we forget these steps already, guys? What did I tell you when we learned dimensional analysis? We're going to use this for the rest of chemistry. We need to know this, okay? We start with what? What we know or don't know?
What we know?
What we know, and what do we know?
We know that there are 2 hydrogen.
That's not what we're given. Well, we are given that too. But that's a conversion factor. We don't start with the conversion factor. We start with what we know.
Grams of
Yeah.
2 and the excess.
10 grams of H2. We're going to start there. Do we know how much oxygen we have?
Unlimited.
But we don't know a number, right? And when we do stoichiometry, when we do dimensional analysis, we're dealing with numbers, aren't we? Okay? So we're just going to convert this until we get grams of water. Like, oh, what do I do? What do I do? What do I do, right? That's when we first feel like when we start learning this stuff. That's why I gave you a mole roadmap. Should we say water is substance A? Or not water, sorry. Is that water?
No,
It's hydrogen gas. Let's say hydrogen gas is substance A.
And we
And
want
what's substance B?
moles. Oh, wait.
Water. We want to go to water, right? That's a different substance. Are you with me? And so, how do we get there?
Moles.
We have to follow this map. We can't go over here. There's nothing that tells us how to convert that, right? We can't go that way. We have to follow this path. Once we get moles of hydrogen gas, where do we go after that? Moles of water, because water we said is B, right? And then once we have moles of water, we go to grams of water. So this is just 3 conversion factors. That's it. We've done that before, right? That's all it is. Okay, so let's do this. Do we want grams in our answer? No, so where does it go?
On the bottom.
On the bottom. We know how to do this. So notice I wrote H2. I didn't just say grams because I'm going to be dealing with 2 different substances. Be organized so that we know what we're dealing with, okay? And I know some of you guys are going to try to make shortcuts. More shortcuts you try to take, the more problems you're going to have, okay? Just trust me here. Until you get really good at this, but even then, I just to make sure you're always 100% true, 100% correct. So we're going to go from grams to what? What's going to be on top? Look at your molar roadmap. Moles. That's all we know how to do, grams to moles. We learned that in the molar mass, right? So moles of H2. And so 1 mole of H2 has a mass of, who can tell me? 2. Use your periodic table. Has a molar mass of 1, but there's 2 of them, right? So that's 2. Are we good? So grams of H2 go away. Now we have moles of H2. If we go back to our mole roadmap, we're right here. And we got to go to moles of water. Okay, so let's see. What goes on bottom?
Moles of H2.
Good, moles of H2, so we can cancel. We don't want moles of H2. What do we want? Moles of H2O. Are you with me? Good? And what numbers go in front of the moles of H2O? Right there. The coefficient in our balanced equation, 2 is in front of H2O, so 2 goes right there. What number goes in front of moles of H2? Also 2, because there's a 2 in front of H2 in our balanced equation. And this is the mole-to-mole ratio from our balanced equation. This is one of these guys that we could figure out, right? Different equation, but okay. Okay. Good? So here we get moles of H2 gone. Are we at grams of H2O yet? That just tells us we keep going. Look at our mole roadmap. We're right here. Oh, we got to go to grams of H2O. How do we do that? Molar mass of H2O. What's the molar mass of H2O? 18 grams per 1 mole, right? 18 grams per 1 mole. Where does 1 mole go? 1 mole of H2O? On the bottom. So they cancel, right? 1 mole of H2O has a mass of 18 grams of H2O. So moles of H2O go away, and we're left with grams of H2O, and that's what we're looking for. That tells us we can stop converting and calculate it. We got 10 divided by 2, multiply 2, divided by 2, multiply 18. Or if you want to do the top first, then the bottoms, that's okay. Or if you want to do the tops, multiply them all and get an answer. Multiply all the bottoms, get an answer, and then divide the 2, that's fine too. Whatever way works for you. We've been going over this since the beginning, right? All I did was the last few days I've given you a lot of different conversion factors. And where can you find these conversion factors? On the periodic table, and I gave you one to memorize right here. Avogadro's number, 6.022 times 10 to the 23 equals 1 mole of anything, right? And then today I given you one more. The multimole ratio found from a balanced equation.
Which is 1:1.
Not always. If it's in this example, it is a 1-to-1. It's a 2-to-2 ratio, which reduces to 1-to-1. It's not always going to be 1-to-1. If we went to oxygen instead to find out how much oxygen we need, here it says we have excess oxygen. But could we predict how much oxygen it really took? Yeah, we could. All we'd do is start again with what we know. 10 grams of H2. This is going to be the same. 1 mole of H2 to 2 grams of H2. So the grams of H2 go away. And now we want moles of H2 on bottom, because we don't want it, and we want moles of O2 on top, because that's what we're looking for, maybe. Maybe we want to know how much oxygen we need. And what's the ratio? Well, there's 2 moles of hydrogen for every, what's that number?
1.
If there's no number, it's a 1, right? And that goes away. And then we find the molar mass of oxygen. For every 1 mole of oxygen has a mass of, you don't have to look at your notes, look at your periodic table. What is it? What's the molar mass of oxygen gas?
15.
It's 16 for just O, but this is O2. So what is it? 32, right? Don't memorize this stuff. I mean, guys, I have a lot of this stuff stuck in my head for doing it so long. But don't try to memorize it and rely just on your brain for stuff that's on the periodic table, okay? That's what I'm saying. I don't care if you memorize that stuff. I don't. But just double check it when you're taking the test, right? Because I know y'all want great grades and stuff, and so just double check everything. So this is 32 grams of oxygen gas, right? And so we can figure out what we got here. So if we figured out this top one should get us 90 grams of water. And what if we figure out, well, how much oxygen do we need? 10 divided 2 is 5. Divide 2 is 2.5 times 32 is, I don't know how to do that in my head. I probably could, but I don't want to have to think so hard. So, what is it?
80.
18?
80.
80? I don't know, is it 80? 32 times 2.5?
32.
You might be right. I just don't want to double check with something we know.
Yeah, it's 80.
Ah, you're good. 80 grams of oxygen. Is that how much we really need, guys? Is that how much it's really going to take? That's if everything goes 100% perfect. When does everything go 100% perfect? Almost never. What am I saying? This is just a prediction. When I say just, it's pretty close. It's going to be pretty close. And unless you are not good at making measurements, right? You measure 10 grams and you really got 15, yeah, it's going to be different. But if you got really close to 10 grams of hydrogen gas, this is going to be pretty close. And I'll show you how to find percent error. Percent yields. I'll show you how to find percent yields. But whether it's percent error, percent yield, or percent anything, it's all the same, right? You guys okay with percentages? Okay? All right. Did I get everybody caught up with this? Do we understand how to go from one substance to a different substance?
Yeah.
Okay? All right. Now, let's show you something that's, well, what if we don't know if we have excess something? I'll show you. Let's start with something real simple, something that we all understand, hopefully. Okay, let's say we have And this isn't chemistry right now. This is just trying to bring it home. Can anybody tell me what these are? Who knows, right? This might give it away.
Hamburgers?
Oh, these are hamburger buns. Okay. All right. So nice. No. Okay. I'm not an artist. I'm a chemist. Okay. So we got 8 hamburger buns. That's how many comes in a pack, right? Have a pack of hamburger buns.
Wouldn't it come in 12?
They might be able to, right? But this bag that we got only has 8. Sometimes they come in 8, sometimes they come in more. But okay, we have 8. And, well, we're going to have hamburgers because maybe some of us like it, some of us might not. Some of us might not even eat them, so that's okay. But let's say we're doing hamburgers, we're having a barbecue, and we go to the fridge to get our tomatoes because you got to have tomatoes, right? Maybe some of you guys don't like tomatoes, but okay. You got to have tomatoes, so let's say we go to the fridge, we only have 1 tomato. But it's a big one, kind of big. There's our tomato-ish, right? And we only have 5 slices. That's all. We should have went to the store. But we only have 5, okay? And we go to the freezer, because we have to freeze our meat, and we buy it at Costco, and the slices, whatever, okay? Make it easy. And, let's say, hold on. We forgot to order more hamburgers. We only have 4, right? And we pull apart the lettuce. We have a little bit of lettuce left. They're not all the same size. That's how it goes, right? 1, 2, 3, 4, 5, 6. Okay, we have 6 pieces of lettuce, right? They're pretty good size. We can put on hamburger, right? And what else you got to have?
Cheese.
Oh, you got to have cheese, right? You have to. Oh, you don't have to. But okay, whatever. And let's say we have 7 slices of cheese because we got a little distracted. Maybe we went camping and we left it in the fridge and it's gone moldy and part of it we had to get rid of. And I don't know, you guys know the deal, right?
Yeah.
Okay, so this is what we have. Hey, how many full hamburgers can we make?
Full hamburgers, that's going to be 4.
Can you guys do this? Is that pretty straightforward? We can make 4 hamburgers. Who limits us? What limits how many hamburgers we can make? Yeah, go ahead.
The smallest number,
Yeah, so which is it in this case?
the patties.
Yeah, the hamburger patties, we only have 4. So if we write down how many we have 8 here, 5 here, 4 here, 6 here, and 7 here. Well, that one limits how many hamburgers we can make.
I mean, you could invite vegans, but then you would have to hang out with vegans.
What's wrong with that? I used to be a vegan. I'm still wanting to, but sometimes I kind of. I mean, if you. Yeah, okay. But yeah, it doesn't matter. Limits how many hamburgers we can make. All right. Dang. Can we take a small break?
Yeah.
All right. So that's what we're talking about here is limiting reactant. Okay. So that was a rate like on a barbecue. Our hamburger patties were our limiting factor, right? But the limiting reagent or reactant, sometimes it's called a reagent to make it harder because science is hard, right? No, not really, but. All right, so the limiting reactant is the reactant that limits how much product is formed. In the case of the hamburgers, hamburgers were the products, right? And all the different parts are the reactants, kind of like, right? But it's not as easy as just looking at the hamburger reactant, the parts of the hamburger, right? It's not that simple. We have to do stoichiometry to figure this out. Okay? You ready for an example? Does that make sense, what I just talked about? Okay? And I'll refer to that hamburger problem as we go. All right. So let's say we go back to this equation. We have 2H2 plus O2 gives us 2H2O. That balanced? Yeah. Okay. So we come back to this equation, and let's say this time we have 10 grams of hydrogen gas, and we also only have 10 grams of oxygen. Now we could probably do this in our head because we just did this problem, right? Maybe I should change the numbers. But that's okay, right? We want to know which one limits how much product we get. Which one limits how much water we can make? Is hydrogen the limiting factor, or is oxygen? Those are the only two parts that make water, right? You with me? Which one has more? Oh, they're the same, right? So, but if we're making a bike takes 2 tires and 1 frame. So they don't all take the same amount. Can we just look at this? Not exactly, because they all have different masses. They have different molar masses. So we can't just look at it and say, yeah, I think it's this one. If we do, we're just guessing. And what happens when you guess and there's only 2 options? 50% chance. And if you're me, then 100% chance, right? So guessing is not a way to go. So we just check this. We want to find out how much water we get. Okay? Well, first of all, we want to find out which one limits, right? But in the end, we want to know how much water we get. So we're going to start with what we know. What do we know? We know we have 10 grams of hydrogen. And we also know we have 10 grams of oxygen. So where should we start? With one of them. Okay? Doesn't matter which one. You're going to have to do them both. Okay? So let's start with 10 grams of hydrogen, because we just did this problem, didn't we? 2 grams of hydrogen, because that's the molar mass of hydrogen for every 1 mole, right? Then what do we do after we convert it to moles? Well, check your mole roadmap. What do we do next? We have moles of hydrogen, but we want to go to grams of water, let's say. We just did this one.
So we have our mole of the one, or particle A, or we have mole A, we need to go to mole B, which is a mole-to-mole ratio.
That's it, mole-to-mole ratio. What's the mole-to-mole ratio? What goes on top, what goes on bottom? Somebody tell me. I don't care who, just somebody tell me.
the solute goes on top, the solvent goes on bottom.
We don't have solvent solutes here. This is just hydrogen gas and oxygen gas making water. Yeah, this is not a solution. 2 of those for every 2 of those. You with me?
Yeah. So
That's
2
it.
hydrogen, 2.
What goes on top? 2? Okay.
Hydrogen.
But what, hydrogen goes on top? Why? Do we want moles of hydrogen in our answer? No. So where does it go? On the bottom. 2 moles of hydrogen for every
2 moles.
2 moles of water. Are you with me? I'm feeling that some of you aren't quite getting this because you're all silent. Is that true, or are you just being quiet because you don't want to talk? That's fine if you don't. Are we good?
We're starting to get there, yeah.
Okay, we okay? All right. So moles of H2 go away. And if we just wanted to find out what the limiting reagent is, we can stop here. But we never just want to go to moles. I mean, the problem on the test might say go to moles, or it might say go to grams. We'll find out. But if you just want to find the limiting reactant, then we can just go to moles. We just have to go to amount of product. What if we have 2 products? Like in the case of the sodium and water problem, right here. We have 2 products here. What product should we go to? The one that we're interested in. What if the problem doesn't say what you're interested in? Then just pick one of them. Don't do both. Pick one of them. You with me? Because if we're having hamburgers and hot dogs for dinner, well, does hamburgers limit how much hot dogs we make? No, right? So you just have to be consistent with going to the right product, going to the same product, I should say. Okay? All right, so do you want to go to moles or just go to grams? We already did this, so we already know the numbers, right? So let's just do it. Okay, so we have, for every 1 mole of water, we have 18 grams of water, right? But again, if the question just asks, what's the limiting reactant? You can go just to moles. Does that make sense, guys? Okay. So moles goes away. Those 2's goes away. So that's 9 times, that's 90. We just figured this out, right? 90 grams of H2O. So if we use all 10 grams of hydrogen gas, we're going to get 90 grams of H2O. Good? We just did this problem. But what if we use all 10 grams of hydrogen gas? Oxygen gas. If we use all 10 grams of oxygen gas, let's figure out how many hot dogs we can make. No, let's go to the same product. We have to go to the same product, and we can't relate them. We can't. Does that make sense? Okay? We don't know. Yeah, we have to go to the same product. So we're going to do 32 grams of oxygen, because this is the molar mass of oxygen, right? To 1 mole of oxygen gas. That goes away. And what's the mole-to-mole ratio from oxygen to water? Try again.
1 to 1.
Try again. Do you have to guess this, guys? No, you don't. It's 1 to 2. There's a 1 in front of oxygen and 2 in front of water. That's it. Don't guess. Look at it. Where does the one mole of oxygen go? Top or bottom? On bottom, so it cancels, right? 1 mole of oxygen gas to 2 moles of water. That goes away. And then we're just going to copy and paste this guy, right? 1 mole of water 18 grams of water. And we do this, and what do we get? 10 divided 32 times 2 times 18. What do we get?
$11.25.
11.25 grams of oxygen. Okay. Sorry, not oxygen.
Hydrogen.
Water, that's all we have left, right? Okay. So again, if you're not writing your work here, you might say oxygen because we're dealing with oxygen, right? You might pull a mistake that I just made. But if you read everything, if you have everything written down, we know everything cancels out except for grams of water. So that's our unit. No questions. Good? All right. So which one, hydrogen or oxygen, limits how much water we can make? Go ahead. Oxygen. If we use all of the oxygen that we have, 10 grams, we're only going to get 11.25 grams of water. So can we make 90 grams of water? We're making predictions here. Can we make 90 grams?
No.
No, we cannot. Because oxygen, we don't have enough oxygen. Does that make sense?
Yeah.
If we have excess oxygen, yeah, we can. But we only have 10 grams. So here, oxygen is the limiting reactant. And what is this called? How much can we make? What's our prediction? This is called our theoretical yield. Our theoretical yield is either 90 or 11.25. What is it?
11.25.
That's it. 11.25 grams of oxygen, of water is our theoretical yield. What does theoretical mean?
Possible, but not.
Based on theory.
Yeah.
Is theory something we can we rely on theory?
No. But it's a reasonable assumption.
We can rely on it. And it's pretty darn close. And why is it not perfect? Because humans are doing it. Okay? It's pretty accurate. Pretty darn close. So our theoretical yield, what's yield mean?
How much you get.
Yeah, how much we make, how much we produce, how much we get. Yeah, all those words are synonymous, right? So theoretical yield is just our prediction. And it's really, let's give a definition for this. This is a maximum amount produced. We can't get any more than that. That's if we're 100% perfect, right? If we're off a little bit, it's going to be less than that. Are we good? So that's kind of like the total, isn't it? Okay? Does that make sense to everybody? Okay. Let's do one more on this same problem. Because that's one question. I might say, what's the limiting reagent or reactant? And our answer is oxygen. Oxygen limits how much water we can make. Good? But maybe another question will be, which one is our excess reactant? Which one do we have more than enough? Which one do we have extra? What? Hydrogen gas. We have way more than enough, right? But maybe our question doesn't say what is the excess reactant. Maybe it says how much excess reactant do we have left over? If we have a lot left over, can we save it? Probably not. It's dispersed, right? So is there an advantage to figuring out how much we can actually need? How much we need? So that we don't waste so much, right? You're wasting stuff, you're losing money. So that's why it's good to do these predictions so that we don't lose money in real life, yeah? Okay, so let's figure out how much extra hydrogen gas we have. Where do we start? Now we have a lot of information. I would always start with what we were originally given. We were originally given these two. Which one should we start with if we want to find out how much hydrogen gas we have left over? Think about this and make a guess. Nobody wants to be wrong. Okay, so we're going to start with our limiting reactant, always. Are we ever going to make 90 grams of water? No. So is this number very useful to us? No, it's not. We're not going to use that. This is our theoretical yield, and this is how much gets used. We use all of it. Well, let's use that. That's the best number to start with. Does that make sense in everybody's mind? Are we good? So we're going to start with 10 grams of oxygen gas again. And we want to know how much extra hydrogen gas we have. So what are we going to convert this to? If we go back to our hamburger problem, how much extra buns do we have?
8? Wait.
4. Oh, how does it do that? We have 8. We start with 8 and we subtract how many we need, right?
Right.
We need 4 of them. We know that just because we know how to make hamburgers.
Yeah.
But is it that easy to do it here? Not quite. We have to figure out how much hydrogen gas we need to completely react with 10 grams of oxygen. You with me? Okay? So we're going to convert this to grams of hydrogen gas. So we're going to do the same thing. We're going to just copy and paste this. We already did the work, right? So 32 grams of oxygen on bottom, so they cancel, to 1 mole of oxygen gas on top. That goes away. And we use the mole-to-mole ratio for moles, so we have 1 mole of oxygen gas to 2 moles of hydrogen gas from our balanced equation, right? 1 here, 2 there. Y'all with me? Good?
Wait, what? Sorry.
So we're just using the balanced equation to go from moles of one substance to moles of another substance.
Okay.
And the coefficient in front of oxygen is 1. Coefficient in front of hydrogen is 2. That's all we do. Are we good? Thanks for stopping me. Okay. And then we use the molar mass to go from moles to grams, right? So we have, for every 1 mole of hydrogen gas, we have 2 grams of hydrogen gas. That's the molar mass of hydrogen gas. And we go 10 divided by 32 times 2 times 2, and we get 1.25 grams of hydrogen gas. What does this tell us? This is our theoretical amount of hydrogen gas that we need to completely react with the 10 grams of oxygen. You with me?
Yeah, it's our theoretical yield.
It's not our theoretical yield because it's a reactant. It's just telling us, since we go to a reactant, this is how much hydrogen gas we need to completely react, so we have 0 leftovers.
Oh, okay. Yeah.
If we need 1.25 grams of hydrogen gas, and we started with 10 grams of hydrogen gas, how many do we have left over? Can we do this? Same thing we did with the hamburger problem. You subtracted it in your head,
8.75.
8.75 grams of H2 in excess. Does that make sense to everybody? Questions? Are we all feeling good about this? Yeah, question, Parker.
You subtract, you're right.
No, are we good? No, really.
Yeah, we're good. I didn't know where we got the 8.
Yeah. We started with 10 grams. Sorry, I didn't show my work. We started with 10 grams of hydrogen gas, and we only use, theoretically, we only use 1.25 grams of H2. And so we get 8.75 grams of H2 left over. Does that make sense? Good? Any other questions? All right. Got a little tiny bit left. Let's review stoichiometry. Step 1. What do we do first? And I told you this, but we didn't. We kind of did it, but I told you I'm always going to do this. What's our first step? Go ahead.
Get balanced equation.
Yeah, we have to have a balanced equation. If our equation is not balanced, then all this work that we just did is wrong. It's not even close to the actual value, right? So we got to have a balanced equation. Balance chemical equation. Okay? We got to have that before we do anything. And for this exam that we're going to be doing in the next week or so, I will give you a balanced equation. You won't have to do that until next unit. Okay? Okay, step 2. What do we do then? Always start with what we know and convert to what? Start with grams of B and convert it grams of A and convert it to
Use
the molar roadmap.
yeah.
So what's our very first step on that?
So we're at grams of B or grams of A?
We could where do you start? A or B?
I suppose A. A would be
Yeah,
best.
it doesn't matter, right? But so if we go to this molar roadmap, go back up to somewhere. Can we start at B and go to A?
Yeah,
Yeah, it doesn't matter. It's the same on both sides. It's just a different substance, right?
but you can't go straight to B
But
to A. You have to
in my mind, I do A before B, but it doesn't matter, right? Okay, so what do we got to convert to? Moles. We have to get the moles. That's our very first step. So convert given substance into moles. Okay? And again, we're just following the mole roadmap. What's our third step? We convert to moles of desired substance. And again, guys, we're just following the mole roadmap here. That's if I, in fact, I'll show you this after we're done here. And step 4, we convert to desired unit. Whether it be grams or moles or milliliters or particles or whatever, right? Are we good with all those steps? Okay. One last thing. and that is percent yield. This is just to say how good we did in the lab, how good we did with this reaction, what our final grade is, right? Okay, and it's just a percent. So how do you do percentages, guys? In general. I'm not talking about percent yield, I'm not talking about percent error, I'm talking about percentages. How do you figure out the percentage of something? Let's say we're taking a test. How do you figure out the percentage? What do you do?
Like for the test, like you would divide like what you got and then.
How many you got right divided by
Like how many like points?
how many there were total, right?
Yeah.
It's always divided by the amount of total, right? Always, always, always. What's the total amount in chemistry called? In theory, what's the maximum we can get?
Theoretical yield.
Theoretical yield. That goes on bottom. What do we go on top? What we actually get from doing this experiment, doing this reaction. We call this the actual yield. Maybe we should write a definition here. So this is percent yield. So actual yield is the amount of product that actually forms. By actually doing it physically, right? And then, how do you find percentage? So we do what we got divided by the total, and then what? Multiply by 100. That's it. So when we did this over here, this right here, this right here was our theoretical yield, right? What if we actually produced 10 grams of water when we did this? We only produced 10 grams of water. How do you find the percent yield?
Well, you take the 10 and divide it by the 11.5.
That's it. Well, we actually got divided by the maximum we can get, the theoretical yield, and then times by 100.
Yeah.
That's it.
So that would be, let's see, what would I have the answer, I'm just calculating the significant figures.
Good.
That would be 88.9.
So yeah, if we actually made 10 grams of water, then we go our actual amount divided by our theoretical amount. Was it 11.25?
Yes.
Okay. And then we times that by 100, just like we do on a test. No different. And what'd you get?
88.9.
88.9%.
That's rounded up from the significant figures.
Okay. Are we good? Do you want to do another example? Because I'm done. We covered everything. But if you need more, should we do one more? Or you're good? How you guys feeling? I don't want to waste your time, but I don't want you to go home and say, oh, crud, that was rough. So, one more? Okay, Leah, let's do it. All right, so this time we have 2C3H8O, which is rubbing alcohol, isopropyl alcohol, plus 9 O2s gives us 6 CO2s and 8 H2Os. So there's our balanced equation. First step's done, right? And let's say that we have 30 grams of isopropyl alcohol and 30 grams of oxygen gas. And we want to know how many grams of carbon dioxide we form. Why? Because carbon dioxide, everybody says this is bad stuff, right? Well, it kind of is and kind of isn't. It's good for the what?
Trees.
Yeah, it's good for the trees, bad for us. But I don't know. Okay. We don't want to breed this stuff, but okay. But maybe we have enough. We don't need to be burning fuel and producing all this. So let's see how much carbon dioxide we make. What do? What does stoichiometry say we do? We have a balanced equation. The first step is done. What's our next step?
Convert to moles.
Convert what to moles?
Well, we're looking for the carbon dioxide.
Yeah. What do we convert to moles?
Oxygen.
What?
Oxygen.
Oxygen or
The one with
isopropyl alcohol? Which one? The answer is both, right? We have to know which one limits how much product. Right? We have to do that every single problem. Even if the problem doesn't say, what is the limiting reactant here? We still have to find it. Because one of those produces a smaller amount, right? And that smaller amount is going to be our theoretical yield. You with me? So we have to do both. It doesn't matter which one you do first. I just start from left to right, but do them both. 30 grams of, and I'm going to write C3H8O. Sometimes these compounds are just huge. It's like, oh, I have to write all this stuff. Yes, do. Write it all. The more organized you are, the more neat you are, the less mistakes you're going to make. Okay, we convert grams of isopropyl alcohol to moles of isopropyl alcohol. You're following our mole roadmap, right? So we got 1 mole of C3H8O on top. What's the mass of 1 mole? 60, good. 60 grams of C3H8O. That goes away. And we're looking for grams of CO2, so let's go to grams of CO2. Well, we can't get there yet. What is the next step on our mole roadmap? Or are you guys doing this by yourself?
The 44.
So, first of all, we have to go from this to what? This. Using our mole roadmap, it says go to mole-to-mole ratio. So what goes on bottom?
CO2.
So does CO2 cancel C3H8O?
60.
Where does 6 CO2 go? On top or bottom?
top.
On top, because that's what we're looking for, right? 6 moles of CO2 on top. How many on bottom?
C3.
How many?
2.
2 moles of C3H8O. Everybody with me so far? Good? And we got to go to grams. We're not there yet, so we keep going. And for 1 mole of CO2, that goes on bottom, so they cancel, right? Has a mass of what? Did you say 44? And that goes away. And we can figure out the theoretical yield if we use 30 grams of isopropyl alcohol, which is 66 grams of CO2. Is that our answer? We don't know yet, right? We got to do one more. So let's start here. 30 grams of O2. And we've done this in plenty times today. So 32 grams per mole is the molar mass of oxygen. Now we use the mole to mole ratio. What goes on bottom? You guys tell me.
Oxygen,
How many?
9 oxygen.
9 moles of oxygen on bottom. We get that 9 from right there, right? 2,
Wait, where did we get the 9 from?
the coefficient of oxygen.
There we are.
This is the mole to mole ratio. Follow our mole road map, right? 2, 6 moles of CO2. We get that from our balanced equation, right? That goes away. And now we do the molar mass of CO2. We're just going to copy and paste that guy right there. 44 grams of CO2 to 1 mole of CO2. And that tells us we get 27.5 grams of CO2. So which reactant is our limiting reactant? Oxygen again, because we produce a smaller amount, right? We cannot produce 66, so we're never going to use this, guys. That was just to see which one it is. So this is our theoretical yield. Does that make sense to everybody? Good? And let's say only 25 grams of CO2 is formed. What is our percent yield? Go ahead. You guys do this. You guys got this, right? So what goes on top?
The actual yield,
Which is,
25 grams.
yeah, we only get 25 grams of CO2. And what's our theoretical yield? 27.5 grams of CO2. What cancels? Everything but the numbers, right? No units. What else do we have to do?
Divide them and
Times by 100% to convert it to a decimal, a fraction to a decimal to a percentage, right? This is what we learned in 3rd grade, right? 4th grade, wherever we learned it, right? And if we didn't, let's make sure we get it down. Percentages are important for everybody in everyday, not everyday life, but everybody uses percentages, okay? So what do we get? About 91%?
90.9.
90.9 rounds to 91. All right. We good? Can you tell me how much extra isopropyl alcohol we have? After this reaction, how much extra isopropyl alcohol? Make a prediction. How much extra would we have?
Could you scroll up a little bit? Thank you.
What do we do? Where do we start? If we want to know how much extra, this is going to be on the test, guys. You have to know how to do this. How much extra isopropyl alcohol? Why do I call it isopropyl alcohol? Because that's our excess reagent, right? How much extra do we have? Who can tell me where we start? Do we start with 30 grams of oxygen or 30 grams of isopropyl alcohol?
30 grams of isopropyl alcohol.
Try again. Why do we start with oxygen? Because that's the limiting reactant. Yeah, we always start there. Always, always, always. That's why we figured that out, right? Always. Write that down in big bold letters. Always start with the limiting reactant. Once we know it, let's start there. So we're going to start with 30 grams of oxygen gas. And always start with what you're originally given. Would it be okay to start with 27.5 grams of CO2? It would be okay. That's our theoretical yield. But what happens in the case that we made a mistake?
Ruins
Then
it.
everything else is wrong, right? Always start with your given amount. Always, always, always. So we don't make more mistakes than we should. Okay, well. Then we're going to convert this to what? We want to find out how many grams of excess reagent we have left over. So we're going to convert 2 grams of C3H8O, right? Okay, so we're going to do 32 grams of O2. This is all repeat. We've done this over and over again today. To 1 mole of O2. And then the mole-to-mole ratio on our balanced equation is 9 to 2, right? So 9 moles of O2 on bottom to 2 moles of C3H8O. And then we convert that to grams, and we don't have to redo it all because we did it right here. We're just going to copy and paste that guy. But flip it, right? 60 grams of C3H8O to 1 mole of C3H8O. That goes away. And what does it give us? 30 divide 32 times 2 divide 9 times 60. Somebody get that for me.
That's 12.5.
12.5 what?
Grams left.
Grams of C3H8O. Is that how much we have left?
Yeah.
Not quite. What is that number?
Oh, left from the.
That's how much we theoretically need, right?
Right.
That's how much we need. How much did we start with?
30.
30 grams. So how much do we have left over? 30 grams minus 12.5 grams is
17.5.
17.5 grams. So be careful when you do all this. You feel like, okay, I got my answer, I'm done. No, that's not our answer. We got to go back to the question. What's the question asking? Make sure we answer the right question. Good?
Mm-hmm.
Grams of C3H8O. And that is how much we have left over. Good? Can we do this? Go home and practice it. If you don't do this on your own, it's not yours. If it's not yours, you're not going to nail it on the test. But if you do, you got it. It's yours. Any questions before we leave? Okay.
I actually do have
Yeah, go ahead.
Can I have a high five?
Yeah, high five. Woo! Got it? Figured
Yeah.
out? Understand it?
Mm-hmm.
Awesome. Okay. Have a great weekend, you guys. And drive safe out there, please.